All right, guys, today I just want to do a quick lesson on how to, set up a galvanic cell, just kind of show how to set up a standard galvanic cell, which is just a battery. All the things you need to be able to represent in the galvanic cell. Um, Identify the anode, identify the cathode, show me the flow of electrons from anode to cathode, and then as the reaction proceeds, what's being produced at the anode, what's being consumed at the anode, what's being produced at the cathode, what's being consumed at the cathode, right? So just understanding the overall oxidation reduction reaction. And then understanding when you have a salt bridge or the electrolyte paste or, however they want to give you a source of ions to maintain charge, just knowing that the positive charged ions from whatever that is, the salt bridge, that's what we'll just call it, go to the cations, go to the cathode as the reaction's proceeding, and the anions go to the anode as the reaction's proceeding. Okay, so just kind of the basics. So it's the warm-up that we are doing in class, but just want to give you a little bit of explanation and point out a few things. All right. So let's get to it. All right, so here's our question, right? So we want to construct a galvanic cell. So here's kind of our setup, our blank setup. So this would be our salt bridge. We got our two beakers, and then over here we got one electrode. Over here we got another electrode. Here's our voltmeter, okay? And we want to make a voltaic cell based on this redox reaction. So so this is the oxidation reduction reaction that's going to occur. So we want to calculate its cell potential so we can know what the voltmeter should read as the reaction proceeds. We want to identify the anode, the cathode, the anode electrode, the cathode electrode, so the metal here and the metal here. The salt bridge, so identify the salt in the salt bridge, all right, and then the initial voltage on the voltmeter, and indication of what gets produced and consumed as the reaction proceeds as the electrons flow from the anode to the cathode, right? So that's the basic idea. So we're going to use Appendix C to figure out this potential first, all right? So let's go ahead and do that. So the first thing is to, kind of identify this as an oxidation reduction reaction and find your two half reactions. So in this, we got aluminum going from 0 to 3 plus. So the aluminum's undergoing oxidation. So this would be the oxidation half reaction for this reaction, right? Aluminum yields aluminum 3 plus, and by producing 3 electrons, right? And then the copper's being reduced. It's going from 2 plus to 1 plus. So the way that happens is the copper 2 plus gains an electron and becomes copper 1 plus. So this is the reduction half reaction, right? So we got our two oxidation, we got our oxidation half reaction and our reduction half reaction. Now to make these add up to the overall balanced equation, we're going to have to multiply this reaction by 3 so that we have 3 electrons here, and that'll cancel out with the 3 electrons there. But the first thing we want to do is use Appendix C to look up the potentials for this, all right? But remember, Appendix E only gives us reduction potentials. So we're not going to find this reaction in Appendix E. We're going to find the flip of it, the reduction of aluminum 3 plus, right? So the two things we're looking up is the reduction of aluminum 3 plus to go from aluminum 3 plus to aluminum. And notice that this reaction is the reverse of that reaction. And then we're going to look up the reduction of copper 2 plus to form copper 1 plus. That's what we're looking at in Appendix E, right? So we would open up our Appendix E, okay? And we'd find the aluminum one. So here's the aluminum one. So the reduction of aluminum 3 plus is negative 1.66 volts. And then if we go down and find the copper one, remember, be careful, it's not this one, it's not copper 2 plus going all the way to solid copper, it's copper 2 plus going to copper 1 plus, but aqueous. And that is plus 0.153 volts, all right? So that's where we get our reduction potentials. But remember, right, we don't have, this is not, this reaction is happening, so that's E red, but remember, we really need E ox to get the overall potential for the reaction, right? If we look at what we're trying to figure out is the cell potential for the overall redox reaction. So we have E red, but we need E ox, right? And really all we have to do to get E ox is flip this reaction, right? So if I go back to my half reactions, here's my aluminum oxidation half reaction, and we flip the sign to positive 1.66 volts, right? So the reduction potential was negative. That means that oxidation potential would be positive 1.66 volts, all right? Notice that we have to triple this reaction so that our electrons completely cancel out. But remember, when we double, triple, quadruple, whatever, multiply a reaction by anything, we do not change the potential. So the E red from this half reaction stays the same exact value even though we tripled the reaction, because remember, potential, electric potential is intensive, all right? So the overall balanced reaction is this, right? The overall balanced reaction is this. And all we have to do is add these two to get the overall cell potential. So that would be our cell potential, and here's our balanced reaction, right? And notice that I only went to 2 decimal places, because when you add, you're limited by decimal places, and our E-ox only had 2 decimal places. Our E-red had 3, but our E-ox only had 2, so we're kind of limited to 2. But I think it's like 1.813, something like that. So, but 1.81 volts to 2 decimal places. All right. So again, if we look at it, right, whoops, wrong thing. If we go back to our Word document here, our warm-up. So if we look at, so now we know what this is, you know, that's 1.81 volts. Okay, so now that's what we know. So that's what's going to display in our voltmeter when we set it up. But now we need to, you know, set up our galvanic cell, right? So for this one, I kind of set it up in the opposite direction, okay? So you kind of have your choice on what you want to do if you had to set up an entire thing. But let me show you all the things you would have to show in your galvanic cell. So remember, this is the oxidation reduction reaction, okay? So I'm gonna make this side my anode. So remember, anode is where oxidation occurs. So if we go back to our reaction, aluminum is oxidized, okay? So because we have solid aluminum in our reaction, and that's a part of the oxidation half reaction, solid aluminum, that's what we're gonna make our anode electrode, solid aluminum. So our anode electrode is gonna be solid aluminum, okay? And to be at standard conditions for a galvanic cell, we would need aluminum 3+ ions in this solution. And so we would start out in standard conditions for a galvanic cell is the concentration is 1 mole per liter for each ion. So we would need 1 molar aluminum 3+ in here. So maybe to get that, maybe instead of saying 1 molar aluminum 3+, maybe we would have 1 molar aluminum nitrate, which would be 1 molar aluminum 3+. But we need to indicate that we start off in the solution with 1 molar aluminum 3+, and our solid metal electrode at the anode compartment would be aluminum, okay? Now again, you had your choice, so we could have made this compartment the anode, and then we would just take everything we drew over here and put it over here, okay? But, you know, I'm just kind of going opposite, so I'm making this the anode and this is the cathode, and remember the electrons always flow from anode to cathode, all right, for a spontaneous reaction, right? So that's my anode, okay? That's what I have going on over here. And my cathode, now what we want to notice for this one is notice in our reduction half reaction, so reduction occurs at the cathode. In our reduction half reaction, we don't have any solid metal. Remember, this was aqueous and this was aqueous. So if we had solid copper in this reaction, we would make this electrode copper, but we don't. So remember, when in doubt, when you don't have a solid metal to choose from your half reaction, you choose platinum, because platinum's not going to react with anything, but it is going to allow for the good conduction of electrons. So we're going to make platinum our electrode here. Now you would really, you know, make any unreactive, good conducting metal, could be it. So when in doubt, go with platinum, all right? So this one's aluminum because we did have solid aluminum in our overall reaction, right? Solid aluminum. But notice we didn't have any other solid metals. So our other electrode we're going to choose is platinum, all right? So in this, we would need 1 molar copper 2 plus to start with and 1 molar copper 1 plus. So we would need both of those at 1 molar in solution to start initially. So when we dip our electrodes into the solution, the electrons would flow from the anode to the cathode, all right? And this is what we would get on our voltmeter, and we know that based on, the values we got from Appendix C, okay? And then let's talk about, as the reaction proceeds, right? Well, where's our source of electrons? Well, the solid aluminum is pushing 3 electrons along the wire here, okay? And as the solid aluminum loses the 3 electrons, it's gonna start dissolving and forming more aluminum 3 plus. So remember, we're starting with 1 molar aluminum 3 plus, but as the reaction proceeds, we're gonna gain more aluminum 3 plus in this compartment. And another thing to understand is the mass of this electrode is going to decrease. The mass of this electrode is going to decrease as we lose aluminum because some of the aluminum any aluminum that gets oxidized is going to kind of break off of the electrode and dissolve into solution, okay? And so as the electrons flow across the wire, they're going to go down through the platinum, and they're going to add on to a copper 2 plus. And 1 electron will add on to 1 copper 2 plus, and you'll yield 1 copper 1 plus. So as this reaction proceeds, the concentration of copper 2 plus in the solution is going to decrease, and the concentration of copper 1 plus is going to increase. They start out at 1 molar apiece because that's standard conditions for a galvanic cell. But as the reaction proceeds, you're going to lose copper 2 plus and gain copper 1 plus. Now, to make this a little bit better, maybe I should have put a 3 here and a 3 here, like 3 coefficients, because for 1 aluminum lost, you're going to reduce 3 coppers, right? If we go back to our balanced equation, for 1 aluminum solid consumed, we lose 3 copper 2 pluses. So again, we might want to keep this as 1 aluminum dissolving, but if 1 aluminum dissolves and forms aluminum 3 plus, then it's really going to be 3 of these yielding 3 of those. All right, so maybe make a coefficient 3 and 3 there. All right. So the other thing we want to understand is what the salt bridge is going to do as the reaction proceeds. So again, we have electron flow from the anode to the cathode, so we indicated that here. Okay, we're kind of showing that this is being consumed as the reaction goes, and this is being formed. Aluminum 3 plus is being formed as the reaction goes, and we're losing solid aluminum. But the other thing we want to understand is the flow of ions from the salt bridge to each compartment. So again, this is the cathode, and think about this compartment's gaining electrons, so it's becoming negatively charged. So to balance the charge, the positive ions from the salt bridge will go here, and the negative ions from the salt bridge will go here, because as this compartment loses electrons, it becomes positively charged. So to balance the charge, this needs to gain negative ions, and this needs to gain positive ions. But remember, cations flow to the cathode, anions flow to the anode. So if this is my salt bridge, and when in doubt, if you have to pick a salt, pick potassium nitrate or maybe sodium nitrate, because we know that those ions tend to not react in solution. There's usually spectator ions, so go with a nitrate salt, okay? And so you could have picked any salt you wanted to and just show that the cations are traveling in here and the anions are traveling in here. And if we wanted to do it kind of stoichiometrically balanced, if 1 aluminum reacts, you're going to have to gain 3 nitrates into this compartment, and you're going to have to gain 3 potassiums in this compartment. So you might want to put 3 here and 3 here to show a little bit more detail. Another thing that I messed up here, and I didn't notice till after I like this line right here is supposed to indicate the water level. The salt bridge would have to be submerged too, so I really should have made the water level kind of up here so the salt bridge was submerged as well. All right, the salt bridge would not be out of solution. If you remove the salt bridge, then the voltage goes to 0 because the buildup of charge stops the flow of electrons. Okay. All right, so that's kind of the basics on how to construct the galvanic cell. Choosing your materials. Remember, if you need a solid piece of metal and one's not in your half reaction, right? We didn't need to use platinum for our electrode for this one because we had solid aluminum, but we needed to choose platinum here because we did not have solid copper in that reaction. So when you have to pick a metal electrode, pick platinum. When you have to pick a salt bridge, potassium nitrate's a good choice because potassiums don't really react with anything in solution, and nitrate ions don't really react with anything in solution. Okay, so those are, you know, good to choose from. All right. So anyway, that's the basics. So we're just going to be doing practice like that in class, and we're going to bring up the Nernst equation, which is just, you know, a galvanic cell that's not at standard conditions, and then electrostoichiometry, which is a stoichiometry with electrons, and that's it for Unit 6. And when we get back from spring break, it'll be Unit 7 and preparing for your final exam / AP exam. All right, so have a good one.